This will be the second half of section 4.3. I thought I'd walk through problem 21 with you just so you can get an idea of kind of the flavor of the rest of the section. Kind of blends the counting principle and the tree diagrams together. So as I read through this problem, it says a couple of plans to have 2 children. Determine the number of points in the sample space and the possible arrangements of boys and girls. This isn't such a greatly worded problem. I have to think of this as like a 2-experiment problem in some sense. Experiment 1 is having the first child. And experiment 2 would be having the second child. And I know that for the first child, there's 2 possible outcomes. I could have a boy or a girl. Similarly, for the second child, I could have 2 possible outcomes, a boy or a girl. The number doesn't go down 1 because you still have an equal chance to have a boy or a girl for your second kid, regardless of what you had on the first kid. So if I wanted to create a sample space to list all the possibilities of having a boy or a girl and a boy, girl, boy, in the order that they're born, there's going to be 4 elements in the sample space. The size of the sample space is going to be 4. So 21A asks me to create or tell the size of the sample space when a couple plans to have 2 children and to list the order of the children in some sense. So I'm going to construct a tree diagram now for the sample space. So for my first branch of my tree diagram, from the point, I'm going to have 2 arrows because there are 2 options for the first child. So I'm going to do the first kid first, which I'll make that the oldest kid. And then that could be a girl or a boy. For the second kid, there's still 2 choices, so out of each one of these letters, I'm going to make just 2 lines or kind of a less than sign. If there were 3 possibilities, I'd make three lines, but in this case, we just have 2 choices. And the second kid could be a girl or a boy, regardless of what the first kid is. So this is the tree diagram, and the tree diagram is what I use to generate the sample space, which is going to be a listing of all the possible outcomes of having a boy or a girl and all the orders that you could have kids. So to get to this G, I have to have that G first and then the second G. So the first item in my sample space is going to be having a girl first and a girl second, or the girl oldest and the girl youngest in some sense. To get to this B, I would have to have a girl first and then a boy second. Just trying to figure out a path to each one of these letters in the far right part of this tree. To get to this G, I need to have a boy first and a girl second. And to get to this B, I need to have a boy first and a boy second. So this is the sample space. When we get to a test, we need the tree diagram to construct the sample space, but what this question part B wants is just the sample space. And the sample space has 4 elements: girl first, girl second, girl first, boy second, boy first, girl second, and boy first, boy second. And I'm going to assume that all of these are equally likely to happen. You're just as likely to meet a couple with 2 kids as I'm having a girl first and a boy second as one having 2 girls. Now I'm going to do some probabilities, and I have the perfect setup. I have a sample space. I know the number of items in the sample space. Every probability question I'm going to answer, I'm going to form a fraction. I'm probably going to put 4 in the denominator because there's 4 items in the sample space. And the numerator is going to be the number of items in the sample space that have the desired characteristic. So what's the probability that the couple has 2 girls? Let me just write this nicely. I'm going to say the probability that the couple has 2 girls, and I'm going to form a fraction. The denominator of the fraction is going to be 4, which is the 4 items in the sample space. The numerator needs to be the number in the sample space that has 2 girls, and the numerator for part C here is just going to be 1 because there's only one of these four that have 2 girls. For For part D, the probability that they have at least one girl, that means one or more girl, the items in the sample space that fit for part D is the 2 girls classifies as at least one girl. The girl-boy classifies at least one girl because there's a girl. And the boy-girl classifies as at least one girl because there's a girl. So the probability that you have at least one girl is going to be a fraction. I know the denominator of the fraction is 4 because there's 4 items in the sample space. The numerator is the number of items in the sample space that have the desired characteristic. In this case, it's 3. So the probability that we have at least one girl would be 3 and 4. And then for part E, let me be lazy and not rewrite this as a probability. Let me just write the answer as a fraction because that's all we really need. When I wrote my key, I didn't take the time to do anything but write the fraction. So part E wants me to find the probability that you have a girl first and a boy second, and that's just this one. There's only one of the 4 items in the sample space that has a girl first and then a boy second. So the numerator of my fraction for this probability is going to be 1, the one element in the sample space that has a girl first and a boy second. The denominator is going to be 4, the 4 items in the sample space. And that would be the answer to 21E. I hate to do all the problems with you for you, but my problem that parallels this has a coin being cost 2 times, and that's not near as hard. So I'm going to walk through 23 with you. If you want to pause the video, if you think you can do 23 without me, I'll write down some of the answers I could do in my head. The answer to part A should be 8. The answer to part 23C is supposed to be 1 and 8. The answer to part D is 3 and 4. And the answer to part E is 1 and 4. I'll get the sample space here in a little bit. So if you want to pause the video and give 23 a try, that would be great, rather than watching me do it, which is kind of counterproductive. So first thing, read through the problem. A coin is tossed 3 times and a sequence of heads and tails is recorded. So there's kind of 3 experiments. The first experiment is you're going to flip a coin for the first time. And there's 2 possible outcomes. It could come up a head or a tail. The second experiment is flipping a coin a second time. And there's 2 possible outcomes for the second experiment. For the third experiment, I'm going to flip a coin a third time. And there's going to be 2 possible outcomes, head or tail. So the number of items in the sample space that I'm going to create for this experiment, which is flipping a coin 3 times and writing whether a head or a tail occurs each time, is the number of options on the first flip, which is 2, times the number of options on the second flip, which is 2, heads or tail again, times the number of options on the third flip, and again that's 2, and 2 times 2 times 2 is 8. So when I go to create the sample space, it should have 8 elements in it. It's a little more complicated sample space because the tree is going to have kind of 3 sets of branches in some sense radiating out, because there's 3 different experiments in some sense. So for part B, I'm going to construct that tree diagram and create a sample space. So from my first point, I'm going to make 2 branches because there's 2 possible options for the first flip. So for my first flip, because there's 2 choices, I'm going to make 2, a branch with a V with 2, or a less than sign with 2 kind of lines coming out of it. Then I need to work on to my second flip, and finally my third flip. For my second flip, because there are 2 possible outcomes, from each of my first flips, I'm going to make I'm going to make a branch with 2, 2 lines. I was so into the 2 here that I didn't even write the right thing down. I should have said, on the first flip, I could have gotten a head or a tail. Sorry about that. Similarly, regardless of what I get on the first flip, on the second flip, I could get a head or a tail. And from each of these second flip results, I'm going to make another less than sign with just 2 lines coming out of it, because there's only 2 options on the third flip. I'm running out of room here. But for the third flip, you could also get a head or a tail. And so this tree diagram has 1, 2, 3, 4, 5, 6, 7, 8 elements in the far right that's going to match up with the 8 elements in the sample space. Now I just have to describe the path to get to each of the far right letters. To get to that H right there, I have to follow this path going H, H, and H. So one element in my sample space, I'll write it nicely in a second, would be getting a head on the first flip, a head on the second flip, and a head on the third flip. To get to this tail right here, I'd have to follow the path head on the first flip, head on the second flip, tail on the third flip. So the second item I'm going to have in my sample space would be head, head, tail. To get to this head right there, I need head on the first flip, tail on the second flip, head on the third flip. To get to this tail right here, I need head, tail, tail. To get to the head down here, I need tail, head, head. To get to the head there. To get to that tail, it's going to be tail, head, tail. To get to that head, it's going to be tail, tail, head. And to get to that tail, it's going to be tail first, tail second, tail third. So these are first flip, second flip, third flip, all 8 items for the sample space. My answer for part B is just going to be all 8 of those sequences there. So head, 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 tail, head, tail, head, head, tail, tail, and then tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. So the answer I'm looking for in part B is actually what the sample space is. And that's exactly what I have there. Now let me start answering the probability questions. Find the probability no heads is tossed. Immediately I know there's going to be an 8 in the denominator of my fraction because there's 8 items in the sample space. The numerator needs to be any element in the sample space that has no heads, and the only element in the sample space that has no heads is the one that has all tails. So the numerator for this probability is 1 because there's 1 item in the sample space that has no heads. The denominator is 8 because there's 8 elements in my sample space. If I go down to part D, if I want to find the probability that exactly 1 head is tossed, the denominator is going to be an 8 because there are 8 elements in my sample space. I'm worried about my answer, but let's see what we have here. Oh, because I looked at the wrong answer, I think. My answer here is actually, I wrote down a wrong answer, but I'll fix it here in a second. Let me get the right answer real quickly here by finding out what belongs in the numerator. What belongs in the numerator are the number of items in the sample space that have exactly 1 head. That's 3 heads, that's 2 heads, that's 2 heads, that's 1 head and 2 tails. That belongs in my sample space, or belongs in the count for my numerator. This, oh, that's no good. That's tail and 2 heads. I can't count that. Don't count that for this. This tail head tail has exactly 1 head. And this tail tail head has exactly 1 head. So if I did this right and I looked in my sample space and I picked out every single element that had exactly 1 head, there's 3 of them, so my numerator should be 3. And the answer to part D, I just took it off my answer sheet wrong. It's 3 and 8. For part And E is not the right answer either. Ugh. The probability that exactly 3 heads are tossed, the denominator is going to be 8 because there's 8 elements in my sample space, and the numerator is going to be 1 because there's only 1 element in my sample space that has all 3 are heads. All the other ones have a tail, or at least 1 tail. So that should be 1 and 8 as opposed to what I had written down. That's everything with the fix. So hopefully, if you pause the video and did this, you realized I was a moron and I wrote down wrong answers because I have this sheet next to me and I must have pulled answers from 21 as opposed to answers from 23. Sorry about that. So your problem 25 is a real classic problem, a sample space that we're going to get to use a lot. And it's a sample space that generally I wouldn't ask you to generate. It's going to be given to you. I don't know that you'd be ready to do problem 25 right now, but if you feel the urge, give it a try. If not, watch me do problem 26 first, and it should inspire you to be able to do problem 25. So for problem 26, answer each part of question 25, but assume the first dice is a 5-sided dice and the second dice is a 4-sided dice. So first, what this experiment is, experiment 1 is rolling a 5-sided dice, and I'm going to write down the number that appears on the face. And the numbers on this 5-sided dice, I'm assuming, are 1, 2, 3, 4, and 5. 5 things can happen when I roll a 5-sided dice. I can get any number from 1 through 5. Experiment 2 for me is rolling a 6-sided dice, a 4-sided dice. And when you roll a 4-sided dice, there are 4 things that can happen. So if I want to find out the number of items in my sample space that are possible when I roll a 5-sided dice followed by a 6-sided dice, there are 5 possible outcomes when I roll the first dice. There are 4 possible outcomes when I roll the second dice. There's going to be 20 elements in my sample space. On your problem 25, the first dice is rolling a 6-sided dice. The second dice is rolling a 6-sided dice in some sense. You have to think of there as a first and a second dice. Even if I roll 2 dice simultaneously, you have to, when you do the sample space, you have to separate it into a first and a second dice. So you're going to have experiment 1 is rolling a 6-sided dice. Experiment 2 is rolling a 6-sided dice when you go to get your answer for part A of 25. And I believe that's going to be 36. So I'm going to figure out my sample space now. My sample space basically is I'm rolling 2 dice and I'm writing the numbers that appear on the dice. So my first go at giving a sample space is going to be less than sign, kind of with 5 lines, because there's 5 possible numbers that my first dice could come up with. And I'm just going to write the numbers 1, 2, 3, 4, and 5. And this is going to be my first dice. If you were doing problem 25, you would have a 6 layered, whatever you want to call that. For my second dice, it only has 4 options. So out of each one of these numbers, I only put 4 branches. You're going to get 6 again. But out of my 1, I'm going to put 1, 2, 3, 4 branches. And I'm going to put the numbers 1, 2, 3, and 4 on it. Let me start generating my sample space. The first element of my sample space is the 5-sided dice comes up a 1. The 6-sided dice comes up a 1. The second element in my sample space is the 5-sided dice comes up a 1. The 6-sided dice comes up a 2. Then 1 and 3, and 1 and 4. I'm trying to get 20 elements, that's 4 of them. Now I'm going to move down to the 2, if my 5-sided dice is a 2, it's still possible that the 4-sided dice comes up either 1, 2, 3, or 4. And the next elements in my sample space are going to be 2, 1, 2, 2, 2, 3, and 2, 4. If the first dice is a 3, the second dice, which is a 4-sided dice, still could come up 1, 2, 3, or 4. That's going to give me 4 more elements in my sample space. A 3, then 1, a 3, then 2, a 3, then 3, and a 3, then 4. Yuck. And then similarly, 4, 1, 4, 2, 4, 3, and 4, 4. And then lastly, 5, 1, 5, 2, 5, 3, and 5, 4. If I count, there's 4, 8, 12, 16, 20 elements here. That's going to be my sample space. I'm going to write this right on, I'm going to write this on another sheet of paper just to make my work a little bit easier. So the sample space that I came up with was rolling a 1 and then a 1. Oh gosh, how do you do this? Rolling a 1 then a 1, rolling a 1 then a 2, rolling a 1 then a 3, rolling a 1 then a 4, rolling a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4. And I'm going to give myself some room and make these branches longer. A 3 and a 1, a 3 and a 2, a 3 and a 3, a 3 and a 4, a 4 and a 1, a 4 and a 2, a 4 and a 3, a 4 and a 4. Make it even longer. A 5 and a 1, a 5 and a 2, a 5 and a 3, and a 5 and a 4. So those are all 20 elements in my sample space. The reason I gave myself a little bit of room is a lot of time when we're doing dice probabilities, we're worried about adding the 2 numbers that come up on the rolls to get a sum. And when that becomes necessary, I will add that to my sample space. But this is a sample space that's good enough for now. Okay, part C, find the probability that a double is rolled. Well, I know my denominator is going to be 20 because there's 20 elements in the sample space. And a double is both numbers being the same. And for my dice probability sample space here, a 2, 2 is a double, a 1, 1 is a double, a 3, 3 is a double, a 4, 4 is a double, and I don't see a 5, 5. So the number that's going to go in my numerator for part C is going to be 4 because there's 4 doubles in here, both dice coming up the same. And then I'll reduce that fraction. My answer to part C is going to be 1 and 5. For part D, this is the part where I need to add up the faces of the dice. Find the probability that the sum of the 2 faces is 7. My denominator is still going to be 20 because there's 20 elements in the sample space. And now I need to go through and find any pair where I add up the first and the second number and they add up to 7. And I'll just go through real quickly and in my head add up the 2 numbers. 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. I'm trying to find pairs where I add up the 2 numbers and they come up to 7. I think that pair right there, definitely the numbers add up to 7. So this pair would be one that I would count for this question because the sum of those 2 dice, 3 and 4, is 7. I would count this 4 and 3 because the sum of those 2 dice is 7. And I would count this 5 and 2 because the sum of those 2 dice are 7. Those 3 elements in my sample space, if I add up the 2 faces that came up on my dice, they add up to 7. Any of the other ones that I haven't marked out in this yellow color, they add up to a number different than 7. They don't get counted here. So the numerator for my fraction for part D is going to be 3 because there's 3 different ones that have a sum of 7. For part E, to find the probability that a sum of 2 is rolled, the denominator is going to be 20. The numerator is going to be any elements in my sample space where I add up the dice and I get a 2. This very first one here, 1 and 1, the sum is 2. And then anything after this, there, 1 and 2, the sum is 3, 1 and 3, the sum is 4. The only possibility of getting a sum of 2 is getting 2 ones. Once one of the numbers is bigger than 1, then you can't. This is the only one where the sum is 2. So the numerator of this fraction is going to be 1, and the answer is going to be 1 in 20. Part F says, are you as likely to roll a sum of a 2 as you are to rolling a sum of a 7? Absolutely not. You're 3 times more likely to roll a 7 than a 2. So this is no. It's easier to get a 7 than it is a 2 because there's 3 different ways to make a 7 and only 1 different way to make a 2. So let me flash back your problem 25. You can pause the video before I write some answers down. I'm not going to write the tree diagram, the sample space. I'll flash it up here. And notice that I wrote all 36, well, they didn't fit on this sheet, but eventually I write all 36 different elements of the sample space. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And next to each and every one of them, I put the sum of the dice just in case I might have needed that sum to do my probability questions. When I just did the problem that I just did, I didn't write the sum of everyone down because I was only worried about the sums of 7 and the sums of 2. It's safe when you're doing dice probabilities to actually list the sums just in case. It just makes your probability computations easier. It's pretty easy to find the sum of the dice because it's just adding 2 small numbers. So in terms of 25B, the sample space has 36 elements in it. You know, it starts off with 1, 1, and then it goes to 1, 2, and it goes to 1, 3, 1, 4, 1, 5, 1, 6. You're going to need lots more room for it. And then 2, 1, 2, 2, 2, 3, 2, 4, all the way. There's going to be 36 items. For part C of your problem 25, I better write down the right part C. For 25 part C, I came out with 6 and 36, which I reduced to 1 and 6. For your part D, the probability that a 7 is rolled, I also came up with 6 and 36, which reduces to 1 and 6. The probability that a sum of 2 is rolled was going to be 1 and 36 for part E. And you're way more likely to roll a 7 than a 2. Are you likely to roll a sum of a 7 as a sum of a 2? Absolutely not. It's way more common to roll a 7 than it is a 2. All right, so give that a go. And just a few more problems to do. I'll walk through 27 and do it with you. And then maybe we'll call that the end of the section. There's one more problem, but I know I don't test on it. I feel like this video is getting pretty long. And after this, I think we'll have enough to do what we need to do for the practice test and the test. So a coin is flipped, which experiment 1 is. Experiment 1 is flipping a coin. And there's 2 possible outcomes when I flip a coin and write down if it comes up a head or a tail. And experiment 2 is rolling a 6-sided dice. And what could happen when you roll a 6-sided dice is you can get any of the numbers from 1 through 6. So there's 6 different possible outcomes when you roll a 6-sided dice. The number of elements in the sample space is going to be computed when I multiply those 2 numbers together. There's 2 possible outcomes when I flip a coin. There's 6 possible outcomes when I roll a 6-sided dice. There's going to be 12 points in my sample space for creating all the possibilities of what you get on when you flip a coin and followed by what you get when you roll a dice. So pause the video, maybe try to construct the tree diagram in the sample space. For my tree diagram, the first branch is only going to have two choices because the first experiment only has two possible outcomes, head or tail. From the head and tail, I'm going to have 6 different branches because there's 6 options on the second choice, which is getting a 1, 2, 3, 4, 5, or a 6. Let me clean up this and make this into part of my sample space. So one of the things in my sample space is getting a head and then a 1, then a head, then a 2, a head, then a 3, a head, then a 4, a head, then a 5, and a head, then a 6. If I do the same thing with the tail, make 6 branches. 4, 5, 6. Without going off the screen, I could put the numbers 1 through 6 at the end of those branches. That's what the dice could come up. And I'm going to get tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. So those are the 12 items in my sample space. Let me just write them up here, or at least I'll try to write them. So I can get a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, a head and a 6, a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, tail and a 5, and a tail and a 6. There's 12 items there that match up with the number of points in my sample space. Feel good about that sample space. Now I'm going to answer some probability questions. When I go to do a probability, the denominator is going to be 12 because there's 12 items in the sample space. To get the numerator, I need the number of items in the sample space that have the desired characteristic. So find the probability that a head is flipped and an even number is rolled. So I need a head flipped and an even number. And those 3 items are the only 3 items in the sample space that fit what they need to fit. The head 2, head 4, and head 6 are the 3 items in the sample space that have a head flipped and an even number rolled. So 3 is going to be the numerator of my fraction. I'm going to reduce that fraction, and the probability is going to be 1 in 4. For part D, I'm going to put a 12 in the denominator because there's 12 items in the sample space. Find the probability that a tail is flipped and a number less than but not equal to 3. For part D, I'm only counting these 2 right here. Those have a tail, and a 1 and a 2 are less than 3. The rest of these either have numbers bigger than 3 or they have heads. So the items that make up my numerator for part D is getting a tail and a 1 or a tail and a 2. That's 2 of the 12 items. For an answer, I'm going to reduce that fraction. I'm going to make it 1/6. And that's it for that problem. There's a problem 29. I'll flash it up on the screen, but not do it. But it's not that hard. So I think you can do it if you want to. Let me scribble down some answers. So if you feel you need extra practice, do this. If you don't feel you need extra practice, don't do it. In terms of the answers, the number of points in the sample space is going to be 6 because the first experiment for this problem is flipping a coin. There's 2 possible outcomes for the first experiment. The second experiment is picking a number out of a hat that contains the numbers 1, 2, and 3. There are 3 different possibilities for the second experiment, so there's going to be 2 times 3 or 6 possibilities for flipping a coin and picking a number out of that hat. And then if I did a tree diagram, I'm going to get a head 1, a head 2, head 3. And I'll let you do that if you want to, but you don't have to. You can skip this problem. And then a tail 1, a tail 2, and a tail 3. So those are the 6 elements that should be in your sample space. For each of the probability questions, I'm going to put a 6 in the denominator because there's 6 items in the sample space. For part C, I need a head and an even number. For part C, there's only 1 element in the sample space that has both a head and an even number. So you're going to get 1 in the numerator. For D, I need a tail and a number less than 3. The items in the sample space that have a tail and a number less than 3 are those 2. that would give me a 2 in 6 probability, which reduces to 1 in 3. So just in case you decided to do that and you want to have an answer to check, I believe that should be the right answer, unless I made some horrible mistake, but I don't feel like I did there. So that's the end of section 4.3. You need to make sure and have 4.3 really mastered pretty well before you go on. Otherwise, you'll start to confuse some topics together. It's kind of like each section in Chapter 4, if it was on an island, I only tested on that section, it might make for really nice test scores, but we sometimes blend, we do problems that look the same and they're a little bit different, and it gets a little bit confusing. So before you move on from this section, make sure you understand it really well so that you can handle the subtle differences when we get to the next section.